forward in our unit here dealing with electrons, that one of the things I think you would hopefully agree, the idea that the electrons are probably the most important one of the subatomic particles. It's not that we're taking anything away from the neutrons and protons, but for our purposes, the electron is what determines all the elements' reactivity. So we tried to label this. Don't worry about this material up here. Okay, that's for the organic chemistry class. And with this, we want you to know what the example of an ionic bond and a covalent bond. And the best way to do that, okay, would be looking at, this is probably the simplest type of ionic bond you can do because it's a metal and a non-metal. And of course, we know that the column is going to be that of number 7 because it's a halogen, and then there's our sodium. And then we satisfied the octet rule. And remember that whatever column these elements fall into, whether they are S block elements or whether they are P block elements, okay, that's one of the things we associate down here, okay, the S, P, D, and F. I think you can see that on there. And I understand there's a glare from over there, but there's only so many aspects that we have control over. So the S block can hold 2, the P block can hold 6, and so on and so forth. That's why we say maximum here. Remember, these are your values for L. Okay, if an element falls in the S block, it's 0, and then P block, it's 1, and then so on and so forth. That's what these numbers mean down here. Okay, so an ionic bond is any metal or non-metal, and we can even do something like this, okay, if we're talking about blood, okay, and this aspect is a molecule called hemoglobin, okay, and of course one of the things we would associate that with is oxygen being in column 6, and then there's our 6, and then the iron has 2 of them to give away, okay, and that would complete that octet for iron 2 oxide. Then as if we were to do water then, okay, one of the things that we had talked about before in class, I read this, it was from a Reader's Digest article. One of the sad things that comes to some of the sulfides, which is also in column 6, okay, so if we're talking about hydrogen sulfide, okay, this is just slightly different than that of iron 2 oxide. Is this right? Technically, yes, but don't do it like that because that's not how the molecule actually looks. Yes, you have satisfied the octet rule, but a better way of doing that is taking one of these hydrogens and placing it over there on the other side. So upon doing that, that means we take this X, put it over there, and then put this triangle over here with that of another hydrogen. And unfortunately, when it comes to hydrogen sulfide, it's a gas that we can't see, can't smell, much like carbon monoxide. And but I would be led to believe that this is a lot more lethal than that of any type of carbon monoxide. It used to be, I think, farmers, when they're putting their silage away, this is a type of gas that's given off as it's starting to ferment inside their silos. I don't think it's as common as it used to be, but again, hydrogen sulfide gas, or sewer gas is what it might be called as well, may be given off in part of that fermentation process. That's why after you fill your silo, you would leave that open for a certain amount of time just because of the amount of gas that's given off in that fermentation process. Okay, so there's our ionic bond. And then as we look at a covalent bond, the simplest one would be that of ethene. If we have C2H4, okay, so we got 2 carbons, and we're going to just do a double bond, which carbon can do, along with why did I put a C there? Which nitrogen can do as well. above and below. So here's our hydrogens then. And what's happening here is these electrons are being shared between one another. Okay, so that's an example of a covalent bond. Typically, it's when electrons are being shared, but it's also probably between two nonmetals. Okay, that would be a covalent bond. Okay, so elements that can double bond, well, we just illustrated. We saw carbon can do it, nitrogen can do it, oxygen can do it, okay, and sulfur can do double bonds as well. And then some can also do triple. There's only two of them that can do that. Carbon's one and nitrogen is the other. Okay? So for our practical purposes, this is what we want you to know for double bonding: carbon, nitrogen, oxygen, sulfur, and then carbon and nitrogen are elements that can triple bond. Okay? So we talked about this already as well. This is just telling you your blocks located on the periodic table, okay? Your first two columns, and then your 3 through 6 in each energy level. So what that means is when we're picking a noble gas, for instance, number 10, so we know that that's neon, that comes from the second energy level, the 2s and the 2p being full. So noble gas configurations are arrived from them two blocks being full. So if we're doing, for instance, we'll say the element phosphorus, okay? So we know that that is element number 15. Remember, we have to go down, we can't go up. So when we start this noble gas core, the 2s and the 2p's are full. Okay, so that also is explaining part of the octet rule because it has the number 8 associated with it. So we move on and say 3s2 and then 3p, and it looks to me like it is 3. I guess I don't know why I looked at the table. You just add 5 and 10, and that gives you 15, so that would have to be right. Okay. Then, I suppose we could leave this up here for talking about valence electrons as well, with the idea of those are the ones associated in the outer energy level. Okay, I didn't like the idea of using phosphorus. Let's go back to, for instance, the simplest covalent bond would be this. It's an exception to the octet rule. It's a diatomic molecule that where these are being shared. Okay, so a valence electron, remembers the electron in the outer energy level. You're using that all the time in the S and P blocks. Okay, you're utilizing the valence electron because of the column that it has fallen into. Okay, so we've already talked about this. We can make those predictions, okay? S and P blocks will give you your valence number. In other words, if we were to do the element arsenic, okay? We'll do the Bohr model for that. Because it is a P block element, we know that there's a couple numbers we can associate that with, okay? So arsenic, number 33, okay? And then with that, we already know that that is in the 4th period and the 3rd column of the P block. Okay, so we're going to utilize these two numbers, 4 and 3. These two numbers are going to appear again because we put 33 in here, and then following the off-bow principle or slide rule, you've been using that all along, you just didn't realize you were utilizing it. Okay, so 1s2, following your slide rule, 2s2, 2p6, okay, 3s2, 3p6. Then this is where this slide rule makes this correction for you that says this has to fill up before any of these 3D block electrons can fall into place here. We're going to put all 10 of them. Okay, so 1, 2, 3, 4. There's our 4. And then the 3 comes from, in the P block only, arsenic is in column 3. So if we add all these together, we've got 10, 20, 28, 30, 33. So that's got to be right. So there's where those two numbers correlate. The third column, that's a valence number, okay? And you could say it's also in column 5. So it have 5 valence electrons. Okay. And then finally, the Hund's principle, or the bus seat rule, since these last 3 electrons went into the P block, okay, we can do 18, so we're up to argon, okay, so that means we go to, this is full then, we go to 4s2, 3d10, and then 4p3. So 18, 20, 30, 33, so that's got to be right. The last electrons fell in that P block. Okay, so we got N, L, M, and S. So this is the 4th energy level. So N is 4. It fell into the P block, which we associate that with this. So values of L, that means that's got to be 1. And then we need to follow Hund's rule, or the bus seat. There's 3 of them. Remember, don't do that. That's not correct because you're not following Hund's rule or the bus seat rule. Okay, so all these empty bus seats need to be filled up first, and then that gives us a value of 1 for M, and it's pointing up, so that is 1/2. So those are your quantum numbers then as well for that of for the orbital diagram. That term had slipped my mind for just a moment. So I'm hoping this helps you, point you in the right direction, since we couldn't be here today. And again, we'll be running down in Del Rapids. Maybe I should get a little higher. But then if I had a little lower, then you don't see the glare off my forehead. My bald forehead. That, in case you're wondering, yes, that is a funny, so you can laugh if you want. Just throw me a bone out in the crowd. Ha ha ha! See, yeah, I know we would do it. Okay, thank you for doing that. So we'll look over this one more time, and looks to me like we'll keep with the schedule. The exam is on Friday, and any questions about these, chances are it may be with these dot diagrams. Anyway, think about what you might want to have asked or answered, and we do have a substitute. It's very good at explaining this, so if you have any questions, there's no doubt in my mind that Ms. Wiebers can do that for you if you choose to ask. So that's all I've got. So, and I know you cooperate, so that's a comforting feeling on my end. So we will catch up to you next time.